We'll stop, and like we usually do, we'll take the exam there around lab time. Okay, so we've been talking about here the last chapter, which is equilibrium, and as we talked about last time, equilibrium sort of involves a certain type of reaction. It's a reversible reaction. So remember that a reversible reaction are those ones where basically we have those arrows heading in both directions. And in this type of reaction, basically, as we talked about, there's really two directions. There's sort of the traditional direction of the reaction where it goes from reactants to products, which is referred to as the forward direction. And in these sort of reversible reactions, though, at some point, once sort of the concentrations of our products basically build up to a certain level, the reverse reaction will actually happen, and our products will actually come together and make some of our reactants, and it will head in sort of the opposite direction, which is the reverse direction. And at some point during this process, what will essentially happen is the rate of that forward reaction will equal the rate of the reverse reaction. So that rate of the forward direction will equal the rate of the reverse direction. And that really is sort of what it means when we reach chemical equilibrium. Again, as we mentioned last time, it doesn't really involve the process where we end up with the exact same amount on both sides. We have the same reactants and products amount of them. It doesn't really mean that. It just means that the rate, as fast as it goes from reactants to products, those products will then sort of reassemble and go back the other way just as fast. And basically, what that does is it locks everybody into place in terms of their concentration. So, whatever their concentration was at that point, if you're looking at pressures, you could as well, whatever their pressures were at that point, they basically will be able to maintain their concentrations and their pressures because just as fast as it goes one way, it will come back the other way. So, everything just sort of becomes sort of balanced in that sense. And again, it doesn't mean that you have the exact same amount of reactants and products. It just means, again, whatever they are sort of at that point, they will lock themselves into place. Now, there's a sort of a relationship that we have that is a constant relationship when a reaction basically reaches equilibrium, and that is capital K here, which is the equilibrium constant. And essentially, we do the equilibrium constant by taking our products to their coefficients divided by our reactants, also taken to the coefficients in the balanced equation. And this sort of relationship, when you do that, does give you a constant value. As we talked about, really the one main thing about that is it does has to basically maintain the same temperature. So, what at a particular temperature, you will get this ratio that will always end up basically being the same number. And that means you could start with, two of A and four of B in one situation. You could start with seven of A and nine of B in another situation. And as long as you sort of keep the temperature constant at the same temperature, it will come to that same ratio. So that's again something that's a little difficult for some people to understand in terms of equilibrium. They oftentimes think, well, I started with different amounts perhaps in this reaction. I shouldn't end up with the same ratio, but it does actually come to the same ratio. The only thing that will really affect the value of the equilibrium constant is temperature. So if you change the temperature, say from 25 degrees to 50 degrees, the value of K for that particular reaction will change. But if you change it from 25 to 50 and kept it at 50 degrees Celsius and did a bunch of different runs or experiments with the same reaction, you will always get the same value of the equilibrium constant at 50 degrees. So when we do this, this value of K does give us some important information. And as we touched upon last time, if we get sort of a large value of K, that implies that when we reach equilibrium, we would mainly have products there. And again, because K is essentially products divided by reactants, if we mainly have products at equilibrium, it should get us a large value of K. Again, just a large number on top divided by a small number gets us a large number. And vice versa, if we get sort of a small value of K, it means sort of the opposite. When we reach equilibrium, we would mainly have reactants present. For the same sort of reason, if we had sort of a small number on top divided by a larger number on the bottom, we'll get a small number, and that will basically what it tells us. What is a large value? So again, 1 is that very big number, and 1 is considered, anything above 1 is considered a large value of k. Anything less than 1 is considered a small value of k. Um, Another sort of important thing about k is, as it says here, it is actually unitless. So when we sort of give the value of k or see the value of k, it is just a number. It has no units associated with it. And it's kind of a nice thing. There's all kinds of different k's, and as I may mention last time, if you take Chem 1B, that's pretty much all you deal with for most of the semesters, all the different types of equilibrium constants. There's things like Kw that we saw earlier. There's also things like Ka, Kb, Kc, Kp, all kinds of different k values, but they're ultimately all the same thing. They're ultimately all just products divided by reactants, and basically represents the same thing. Any questions on sort of any of that stuff we talked about last time? I think as well, we sort of finished up as sort of talking about ways you can sort of manipulate the K value. Again, sometimes you need to reverse a reaction. And remember, if you reverse a reaction, you basically take 1 over the K value. We also talked about in certain cases, you may have to multiply a reaction by a common number. So for example, if you need to multiply this reaction that we're looking at by, say, 2 all the way across, what that would do to the K value is you actually then would square it. If you had to multiply by 3 all the way across, you would then cube the K value and so forth. And vice versa. The last thing that you typically have to do sometimes is you have to maybe divide by a common number. So perhaps we had to divide by this equation by 2 all the way across to get us an equation we're actually looking for. You then would take the square root of the K value. If you divided by 3 all the way across, you would take the cube root and so forth. So those are very common sort of ways that we sometimes have to manipulate K values. And the last sort of common way is if you have multiple reactions, you can sort of add up each of those reactions and you cancel out whatever's on opposite sides of the arrow. And to get the K value for a reaction where you added multiple reactions together, we actually multiply the K values together. So I think we talked about that at the end as well. So when we talk about concentrations, obviously, if we wanted to solve for the value of K here, we would need the equilibrium concentrations. And for our class, in most cases, that would probably be the equilibrium concentrations you're given. Other classes like 1B, you're not necessarily given the equilibrium concentrations, you're given initial concentrations. But if you needed to calculate something like K, you do want to make sure that you put in always equilibrium values in there. And concentrations are typically given in molarity, and that's usually sort of the unit that we use. I think I might have touched upon last time. You could also do something known as a KP, where you use pressures, works the same way, basically. All right. So calculate the equilibrium constant K from the reactants and products. Calculate K at 127 for the following equilibrium concentrations for ammonia and each of these. So we'll just kind of do this one together. Obviously, we would want the equation, which I think we saw earlier. I think that's what we wrote our equilibrium expression for. But we have basically N2, right, plus H2. Going to make ammonia, which is NH3, probably a 2 there and a 3 there is necessary to balance it. Again, if we were to write our expression, it would be our products over our reactants. So it would be the concentration of NH3, and we do need to square it because of the coefficient that we see here. And remember that the brackets that we see means concentration, and usually what that means is molarity, which is moles per liter. And that would then be divided by our reactants, which would be the concentration of N2 and the concentration of H2. And again, here we do need to cube it as well because of the coefficients. So that's really important there. Any questions on that so far? All right. So, and again, the 3 coming from here. At this point, if these are the equilibrium values, we can literally just put it into our expression here. So our NH3 at equilibrium, 3.1 times 10 to the minus 2. Again, we want to square it, divided by our N2, which is 8.5 times 10 to the minus 1, and our H2, which is 3.1 times 10 to the minus 3. And again, here we want to cube that guy. And if we do all that good stuff there, let's see, 3.1, make sure you use your exponent button, minus 2, and we want to square it, divided by 8.5, exponent button minus 1, and divided by 3.1, exponent negative 3. And again, this one we want to cube in this particular case. And it looks like that we end up with something like, we'll call it 3.8, 2 sig figs, since everything looks like 2 sig figs. 3.8 times 10, it looks like 1, 2, 3, and 4. So 3.8 times 10 to the 4 would be our equilibrium constant value. First off, any questions on the calculation part there? Just for reference here, this is obviously like 3,000-ish or so. That is a very large value of K, which means when we reach equilibrium, we would expect to have mainly products there. That's actually a pretty large value of K. So almost, this reaction is almost 100% going that way, but some of it is still coming back the other way. But this value does tell us that we would expect a lot of NH3 at equilibrium. Any questions on that there? Okay. And here's those steps in case you want to look at it later here. Hopefully they end up with the same number we did there. There we go. Perfect. All right, so why don't you try this one then? Calculate the K for the Okay, so this is the reverse of the reaction that we just did. So previously we just calculated that the K for this reaction was 3.8 times 10 to the fourth. And that really is from a K expression like it was written there, NH3 squared divided by our N2 and our H2 cubed. The reverse reaction would look something like the opposite way, where this would be our reactants, and these guys here would be our products, which means if we wrote the K for the reverse reaction, it would be N2 times H2 cubed divided by NH3 squared. And the relationship, as we talked between both of these, is that is basically 1 over the K value. It's the inverse of the K value, which means since we already have the number, we basically can find the K value by taking the K of the reverse reaction will equal 1 over the K of their forward direction. And that would then give us 1 over 3.8 times 10 to the 4. And that will get us something like 2.6 times 10 to the minus 5, I believe, in this particular case. So remember that if you reverse a reaction to find the K value for the reversed reaction, you take 1 over the original K value, because ultimately, as you can see there, they are basically inverses of each other, that guy related to that. Any questions on that particular one there? And obviously, as it says, if we didn't already have the number, you would just plug in, obviously, the appropriate numbers into this expression here. And obviously, it would get you the same value. Any question on that particular one? All right, try another one here. And see what you come up with. Okay, so on this one, we are looking for the value of K. We have the equilibrium concentrations given to us. So we do want to start with the expression. So that comes from the actual equation here. So K in this case would be our product. So it would be the concentration of NO2. Again, here we do need to square it because of the 2 that's there for the coefficient. We want to divide it by our N2O4. We don't have to do anything to it because really the coefficient here is 1. So it's basically like having 1 there, so we don't have to worry about it. At that point, since these are equilibrium concentrations, we basically just plug and chug it into here, and that would get us on top there, 0.06, again, squaring it, divided by our 0.055, and I believe we wind up with, looks like 0.065, which looks like D, perhaps. Any questions on that calculation there? This also tells us if we were to sort of look at this value, this would be considered a small value of K, and we would expect when we reach equilibrium to kind of still have a majority of reactants present at that point. Any questions on that there? All right. So try this next one, see what you come up with. We got at a given temperature, the equilibrium value is 50. Calculate the equilibrium concentrations of H2 and I2 and HI having the following equilibrium concentrations. I think I read that really badly, but I'm pretty sure you understand what you're trying to find there. I think we're looking for H2's concentration at equilibrium. Okay, so let's take a look and see here. In this particular case, we're actually looking for an equilibrium concentration of H2 at equilibrium. We're given the other 2 equilibrium concentrations, which means we can use our equilibrium expression to do that. You do want to make sure, again, that your equation is balanced, and it doesn't look like they put the 2 here, but you should have a 2 here to balance it. Again, that's going to be important for equilibrium expression because without it, you won't be squaring the HI. You'll obviously get the wrong answer. So I would say in most cases it's probably going to be balanced, but like usual, if you don't see any numbers, you should take a quick look and just make sure that it is balanced. And in this case, it wasn't. So we do need that 2 there. That will give us the proper equilibrium expression, which would be, again, our products, which would be HI. And again, because of that 2, we do need to square it, divided by our H2 and our I2. And in this particular case, they told us the value of that is 50. So at this point, we do have the HI concentration given to us. We do have the I2 concentration given to us. So really what we need to do is solve for the H2. So just kind of putting our numbers in. I'll go down here, I think. So for our HI, it is 5 times 10 to the minus 1 squared, divided by our H2, which is what we're looking for, and our 1.5 times 10 to the minus 2, and that's going to equal 50. If we do some rearranging, basically this guy and this guy switch places, and we end up with something like 5.0 times 10 to the minus 1 squared divided by 50, and 1.5 times 10 to the minus 2 would equal our H2. And again, to get us there, what we did was we multiplied both sides by H2. Those canceled, and then we divided by 50 to the other side. And that's how we ended up there, basically. Those guys would cancel. So that's mathematically how we got to there. And if we put in all that numbers, or all those numbers there, we end up with squared divided by 50 divided by 1.5. Looks like we'll call it 3.3 to the minus 1. Now, because this is a concentration of H2, we do need the units of molarity. It would be the same units as everybody else. So this is not a K value that we're solving for here, but it is a concentration, and it does need the units. And again, it would be the same units as everybody else. Any questions on sort of that part there? So obviously, as you can see here, in addition to just straight solving for the equilibrium value, you can, if you have some equilibrium concentrations, figure out what somebody else's equilibrium concentrations. But again, in this particular one, since they decided not to balance it for you, just take a second to make sure that the equation is balanced before you continue on. Otherwise, again, you will get obviously not the right answer. So here's all those things we just did in separate slides, so you could kind of just see it if you like later when you're watching this to go to sleep or something, you know. Okay. And it's good. They got the same number and about the units. Perfect. Right. Any questions on sort of equilibrium uh, constants, how to solve for K? Again, how to use it like we just did there to solve for any of the other guys. Really, the important thing is to remember it does need to be equilibrium values and not initial values when you put those things in there. All right, so I think we've kind of talked a little bit about this last time, but let's just kind of go over just to make sure. When we talk about equilibrium, they're sometimes described two ways. One is described as sort of a homogeneous equilibrium, and that's very much like a homogeneous mixture. If you remember, in a homogeneous mixture, basically everything looks the same throughout, right? So when we talk about sort of a homogeneous equilibrium, what we're talking about is everybody's in the same phase. So when you look at a reaction, everybody's in the exact same phase, either solid, liquid, gas, aqueous, something like that. So if you look at the top one, the one that we've been dealing with, the N2 and the H2 and the NH3, that's a homogeneous equilibrium. Everybody's in the gas phase, so everything's good. On the bottom, everybody's also in the same phase. They're all in the aqueous phase, and that also is a homogeneous equilibrium. Now, not always will you have sort of a homogeneous equilibrium. You will have sometimes a heterogeneous equilibrium where everybody is not in the same phase. And let's take a look at a couple of those here, I think, on the next slide. And these are some examples of some heterogeneous equilibrium. And much like a heterogeneous mixture, where you sort of see different layers, different phases, same idea here. Everybody is sort of in different phases. Not everybody, but there are different phases happening. There's more than one involved. So we look at the top one, which is basically a decomposition reaction. They're both basically decomposition reactions. First one, we have solid that goes to solid and gas. The second one there is we have liquid that goes to gases in terms of that. And as we talked about previously, when we deal with equilibrium, especially when we deal with heterogeneous equilibrium, there's really kind of two things that are not included in the equilibrium expression. And as I mentioned last time, we do not include things that are solid or liquid in the K expression. And for a couple of reasons, things that are solid, they're basically just kind of sitting there like a rock, and they're really not participating in anything. In order for them to perhaps participate, they would have to become, say, aqueous, and they're no longer solids and stuff like that. So anything that's a solid is not included in the equilibrium expression. Anything that's a pure liquid is not included either, because things like water, for example, in the liquid state, its concentration pretty much remains constant throughout the reaction. It doesn't change very much at all. So they're not included. So as we talked about last time, pretty much what that leaves you is essentially we do include things that are gases and things that are aqueous. So these two guys are things that are included in the equilibrium expression. Again, gases are moving around and flying around, which means they're going to probably cause reactions to occur and participate in the equilibrium. Things that are aqueous basically means a lot of times that they are ions and they're floating around in the solution, which means they're floating around, they're ready to react, they're good to go, and those things do have an effect on the equilibrium. Also a reminder that the difference between L and AQ is L is just a pure liquid. So L would be something like water all by itself, nothing else there. AQ is basically when you make a solution. So that's when you take something, say, like water, and dissolve in it something like sodium chloride, and you make a sodium chloride solution, which is NaCl aqueous, and that implies that there's water and sodium chloride ions basically floating around in the solution. So how this affects is, as I mentioned, I think last time, if we were to write the equilibrium expression for this first guy, it would be K is equal to O2 cubed. This would not be included, and this would not be included. That would be the entire equilibrium expression for it. Same thing if we came down here to this guy and we wrote the K value, it would be our products, which would be H2 squared times O2. And again, this being a pure liquid would not be included in it. So this would be the equilibrium expression for the bottom guy there. So we don't include the S's or the L's in our expression. Another kind of interesting thing that sometimes happens is potentially possible. You could have, say, something like 2A gas goes to, say, be solid. And if you needed to write the equilibrium expression for something like this, K would be 1 over A squared. So if you happen to end up with everything on the product side that's solid or liquid, you would just go 1 over the reactants for your K value, and that's how you would write it. Question on that one. So as you can see here, that's essentially all that would be included in the expression. Again, things that are solid, basically just sitting there, not going to participate in it. All right, so why don't you take a second here and what is the equilibrium expression for this reaction and see which one you come up with. Okay, so same idea. We're going to go products over reactants here. So our calcium is aqueous, so that can be included. Our fluoride also aqueous. We do need to square it because of the coefficient. Coming to our product side, we have a solid, so not going to be included. So this should be our K expression. Looks like D is a winner, I think, on that one. Any questions on that one there? And there's a whole set of sort of equilibrium expressions, as we might see at the end of here, that does involve reactions like this, where on the reactant side, it's all solid. So it always just kind of products. Just to finish up for today, talking about a couple of things we mentioned earlier. Again, when we do see that K, it is specific for the reaction the way it's written. It's specific for that reaction the way it's written in terms of what is on the reactant side, what's on the product side, and for the temperature. And again, we could use that value to help us determine sort of what we would expect to be there at equilibrium. So as we mentioned a couple of times already, if we do get that sort of large value of K, which means basically over 1, so anything with sort of a positive exponent, anything above 1 is considered large. And that means, as we've talked about, basically because K is products over reactants, large value means probably have a big number up on top, and that means we should expect mainly products at equilibrium. And if you have a really, really big value of K, like in the thousands, hundreds, it almost means that 100% goes to the right. But again, it is reversible, even if it's a super large value of K, and it means almost 100% of it's all going to the product side. It is still ultimately a reversible reaction. So a super small amount is still coming back the other way. So, sometimes we think about it, some of these guys, as really large values, and it's a one-way street, but it ultimately is still a two-way street going in both directions. And as I mentioned last time, if we have something that's a small value K, again, that's going to mean that we have a larger value on the bottom, and we should have more reactants on bottom, and we should expect reactants at equilibrium. So here, if the equilibrium rises to the right, the K value here is going to be large, right? So if the equilibrium lies towards the product side, we would expect a large value of K. You don't have a clicker, so don't press anything, I suppose. If we hit the one that goes to the left, that means we mainly have reactants and we would expect a small value of K. Any questions on that there? Okay, I think it's probably a good place to stop. So we'll stop here. We'll leave Le Chatelier's principle for Wednesday, our final day of lecture, I think. And I think we're probably doing Le Chatelier's principle lab as well on Wednesday, so that will all work out pretty good. Reminder that we do have exam 4 coming up on 15 and 16.